In this video, we're going to talk about evaluating limits analytically. Let's start with the basics. So in this theorem here, I've got three different rules. B and C are going to be real numbers, and n is going to be a positive integer. So this first rule states that if I have a limit of b, so remember that's a number, as x approaches c, also a real number, that's going to be an output of b. So that's like this example here. So the limit of 3, which is the same as y equals 3, as x approaches 2, always going to be 3. The second rule is the limit of x, so that's the same as y equals x, as x approaches c, again some number, is always going to be c. So if I had x as x approaches -4, the answer there is going to be -4 because it's the line y equals x. Then the third rule here is the limit of x to the n, so our exponential, as x approaches c, again a real number, is going to be that c to that same n power. So for example, if I had x squared as x approached 2, that's going to give me 2 squared or 4. And along with those three basic rules, there are some basic properties of limits that are outlined here. So, assuming that b and c are real numbers and n is a positive integer, just like before, we're going to have two functions here, f and g, and let's say that the limit of f of x as x approaches c is capital L, and for g of x, that's going to be capital K. And you can look at the rules here. They're pretty straightforward. And they help us figure out what happens when I multiply by a scalar, which is just a regular number, finding the sum or difference, the product, the quotient, or the power of a limit. These rules are very, very helpful. So let's jump into some examples. So let's find the limit of 4x squared plus 3 as x approaches 2. Something to note here is that there's not a denominator and there's not really a restriction or something that x can't be. So what I use in those cases is what we call direct substitution. And what that looks like here is plugging 2 in for x and ending up with 19, which is actually the output when I input 2 into my graph of this polynomial. So our limit here is 19. So our last example was a polynomial function. So this rule tells us that we essentially do direct substitution. We plug in c where x is, and that's what we get. And that's what we got in the last problem. Now let's talk about a rational function. So that's when you have a variable in the denominator of a fraction. Not so pretty. So let's say that I have this rational function here. Normally, I have to restrict the domain because some number for x will create a 0 in our denominator, which is something we don't want. So -1 would be the restriction here, or the break in the domain. Luckily, our limit is x approaching +1. So that means that I can use direct substitution for this guy to solve for the limit. And when I plug in 1, I'm going to get 2 as my resulting limit, which is actually the point on the graph. Now would be a good time to say that you're going to see a lot of theorems in this video if you haven't figured that out already. So these two I'm going to put together because one of them is involving a radical, which just says that if you have some radical here, so the nth root of x, as x approaches c, and c is just a number, you're going to take the nth root of c, and that's going to give you your limit. And then the limit of a composite function is when you put one function inside of the other. So if you have some composite function like f of g of x, you're going to find the limit as x approaches c of g of x, and then take that, so the answer there is L, that's why they use that here. You're going to take that and put that into the function for f, and that's going to be your limit. Now, as much as I love a good theorem, as much as the next mathematician, I prefer worked out examples. So let's do one. Let's take the limit of the cube root of this function as x approaches 3. Now this is a radical and a composite because I have 2x squared minus 10 inside the cube root, which is a composite, and I have a radical. 2 birds, 1 stone. All right, so this 3 is not going to break the domain under here. So I'm just going to use direct substitution to find the limit. So I plug in this 3, I work it all out to be the cube root of 8, which is just 2. So my limit is 2. When I make a promise of more theorems and rules, I deliver. So let's look at 6 more that have to do with trig functions. Now, c is a real number in all of these cases, and really what you're doing is you're taking the limit of some sine, cosine, tangent, etc. function as x approaches c, and you might notice that you just plug in c wherever x is and go from there. So I'm going to work out these 3 examples, we'll run through them, and move on to the next rules. So my first one, I just plug in 0 to where x is. I carry it out using sine and cosine, unnecessary, but it ends up being 0. In the second one, I split up the x and the cosine of x as different limits as x approaches pi. Plug in pi, find that to be negative pi. And then for this last one, I rewrite it as sine x to the power of 2. I plug in 0, and I get 0 in the end. Our next theorem helps us find strategies for finding limits where we can't necessarily use direct substitution. So this next one is functions that agree at all but one point. So if I have 2 functions, f and g, and they're the same, and as they both approach c, that's going to mean that their limits are going to be equal. We'll do an example of that in just a moment. So some strategies to finding limits are here. Try to recognize first and foremost, if you can substitute directly right in, like the examples that we just did, do that. Always try to do that first. Saves you so much headache. Then, if it can't be evaluated by direct substitution, there's a bunch of other ways that you can move forward. So let's start looking at those. So this example of a limit of this function as x approaches 1, can't use direct substitution because if I plug in 1 here, that zeroes out my denominator. So what we can do is take this and try to factor it out first. See what happens. So the first thing that I do here is I factor the numerator. So x cubed minus 1 is a difference of cubes. If you don't know the sum and difference of cubes formulas, look them up, know them, have them in your back pocket. So I can factor out an x minus 1, which actually cancels with the x minus 1 in the denominator. Wow. And so I'm left with the limit as x approaches 1 of this quadratic. I plug in 1, I get 3. And as I graph this thing, this original function here, that is going to have a hole at x equals 1, but the limit is going to approach 3. So that verifies what I have for my answer there. So that last technique and this one is technically called dividing out, which is just factoring the top to see if you can't factor out and cancel the denominator that we have here. So you'll notice that this limit is as x approaches negative 3. And if I plug that in there, that's going to zero out our denominator, which is a problem. So I can't use direct substitution, but I'm going to factor and divide out and see if I can't find the limit that way. So I factor out my numerator and I find that x plus 3 cancels on the top and the bottom, or the x plus 3 divides out. And so I'm left with the limit of x minus 2 as x approaches negative 3, plug in negative 3, direct substitution, and I get negative 5, which also is what appears on my graph over here. And side note, if you were wondering, oh, do I have to write the limit as x approaches blah, blah, blah each time? The answer is yes. Until you have directly substituted, you have to write the limit each time in front. I know it's annoying, but just do it. Thank you. Our next technique is a little less intuitive. So this one is called the rationalizing technique because we're going to need to rationalize the numerator of this example. Why? Because direct substitution is not going to work. 0 plugged in here zeroes out the denominator. So if you think all the way back to Algebra 2 or even pre-calculus, you had to rationalize things that had radicals in them. And what I mean by that is you take the same radical, don't change what's underneath it, even if it has a plus or a minus sign, don't change it. And then you only change that sign. So that's going to be the square root of the quantity x plus 1 over the same quantity on the bottom. So that's going to get rid of those O and I terms when you FOIL. Remember FOIL? So let's multiply all this out. So what I'm left with is the quantity of x plus 1 minus 1 in my numerator, so those ones cancel, and I'm left with an x over an x, so I'm going to divide that x out. leaving me with 1 over the square root of the quantity of x plus 1. Now I'm ready to plug in my 0, get rid of this limit as x approaches 0, and I'm left with 1/2. So that's my limit, and that's actually my result here, where that hole is located at y equals 1/2. So this is the last theorem I'm going to throw at you for now. So let's take two special trig limits that are really useful. One is the function of sine x over x, and the other is 1 minus cosine of x over x. Now I'm going to take the limit of both of those as x approaches 0, and the first one's going to equal 1, and the second one's going to equal 0. Now, take my word for it, there is a proof in our textbook. It's actually proved by the squeeze theorem, so if you want to look that up, go for it. But let's take two examples. The first being this one right here. So let's say my function is tan of x over x, and we're going to take the limit of that as x approaches 0. First thing to note, can't directly plug that in there because that would zero out my denominator. So let's see if we can't break this up. First thing I'm going to do is turn tan of x into sine x over cos x. I'm going to split those two up, and I'm actually going to put the x underneath the sine because of this little rule here. So I replace that with 1, and I find 1 over cosine of 0, which is also 1. Multiply them together, and I get 1, which is also my result right here on the graph. And here's our final example. So let's say we have this function sine of 4x over x, and we're going to take the limit as x approaches 0. Again, can't directly substitute because that would zero out our denominator. So let's see if we can turn it into one of these rules. So what I'm going to actually do is multiply this function right here by 4 over 4, which is the same as 1, not changing anything. So I'm left with 4 out front here and 4 in front of this x on the bottom. I'm going to factor out of 4. So the 4 is here, and based on the rules that we saw at the beginning of this video, I could just pull this out because it's a scalar. So that means that I have 4 times this limit as x approaches 0 of this function. So I have 4x and 4x here. I'm going to replace that with some other variable y, and look at what happens. It's the same rule as up here. So sine of the same variable over the same variable gives me 1. So that's 4 times 1, which is the same thing that this graph gives me. So the answer to this, the limit, is 4. That's going to do it for this video. Thanks for watching.